Bismillahirrahmanirrahim. In this module of Convex optimization course, we will continue our discussion on duality. In particular, we will talk about Lagrange dual problem formulation. We will talk about the concept of duality gap. Later, we will talk about Slater's condition uh, that establishes strong duality. And then I will also review a couple of examples. So let's quickly recap so what we discussed in the last module. So in the last module, so we learned about three concepts. So we talked about a primal optimization problem, and then we talked about Lagrangian function. Using Lagrangian function, so we looked at the formulation of Lagrange dual function, and then we showed that Lagrange dual function serves as a lower bound on the optimal value of the primal problem. So we started with a primal optimization problem, and that does not need to be convex. For this primal optimization problem, we constructed a Lagrangian function that is noted by L is a function of x, lambda, and mu, and which we constructed Lagrangian function by appending the objective function with a weighted sum of inequality constraints and a weighted sum of equality constraints. And we also showed that this Lagrangian is affine in lambda and mu for fixed x. And then using this Lagrangian, we determined Lagrange dual function. So we defined Lagrange dual function to be a pointwise infimum of the Lagrangian over x. And we also showed that the Lagrange dual function is concave in lambda and mu, since it is a pointwise infimum of Lagrangian, which is an affine function in lambda and mu. And then we also showed that this Lagrange dual function serves as a lower bound on the optimal value of the primal problem. So, and that is that G lambda mu is less than or equal to P star for when lambda is in the non-negative orthant, or when lambda is positive, when lambda is greater than or equal to 0. So this G lambda mu is a lower bound for any value of mu and for lambda greater than or equal to 0. But the question here is that what is the best lower bound? Okay, before we start answering this question, so we note here that G lambda mu is a concave function of lambda and mu. So if we maximize this Lagrange dual function, so the maximum value of the Lagrange dual function would be the best lower bound on P star, right? So we're interested in maximizing a Lagrange dual function, because maximizing Lagrange dual function would give us the best lower bound, right? So let us define, in fact, let us formulate this maximization of a Lagrange dual function as an optimization problem, right? And in fact, we call this problem as Lagrange dual problem. So before I formulate this Lagrange dual problem, let me quickly review all of this graphically, right? So we say we have the value of P star, and we draw Lagrange dual function, which is concave. So we have this G lambda mu, this is a concave function, and you see here that every value of G lambda mu is less than or equal to P star, but we're interested in the best lower bound, or this value which is very close to P star. And in fact, we call this value G lambda star mu star, or when you maximize this concave function, or the optimal value of this maximization problem would be G lambda star mu star, and this G lambda star mu star is the best lower bound on P star. Okay, now let us define this as an optimization problem. So we say that we want to maximize this function, this Lagrange dual function, subject to, do we need some constraints? We obviously need some constraints. So if you remember, so this g lambda mu is a lower bound when lambda is greater than or equal to 0. So we should maximize g lambda mu, concave function of lambda and mu, subject to lambda greater than or equal to 0. So this is the constraint here. So this is in fact a convex optimization problem. So because we are maximizing a concave function, and this is equivalent to minimizing negative of this, which is a convex function. So we say that this problem is a convex optimization problem. And the feasible set for this convex optimization problem is given by, let me define feasible set. Feasible set F, and that should be equal to the domain of Lagrange dual function and lambda greater than or equal to 0. When we solve this optimization problem or this maximization problem, and we get the optimal variables lambda star, mu star, and we refer to those lambda star, mu star as optimal Lagrange multipliers, and we also call them optimal, so dual optimal variables. So this lambda star, mu star, when you evaluate this Lagrange dual function at lambda star, mu star, in fact what you get is this value here. So for lambda star, mu star, Lagrange dual function provides us the best lower bound on P star. And let us denote this value of the Lagrange dual function by this D star. So this is D star represents the optimal value of the dual problem. And if you represent this on this graph, so this D star is in fact this D star is equal to G at lambda star mu star. By solving this Lagrange dual problem, this maximization problem, we obtain D star, and D star is the best lower bound on P star. But the question here is, how close is D star to P star? To quantify the closeness between D star and P star, let us introduce the concept of duality gap. So we started with a primal problem, and for a primal problem we can form a Lagrangian, and we can have a Lagrange dual function. By maximizing the Lagrange dual function, we refer to this as a dual problem. So this primal problem may or may not be convex, but this dual problem is always convex. And the optimal value of the primal problem is given by P star, and the optimal value of the dual problem is given by D star. So, and what we know from our earlier analysis that D star is less than or equal to P star. In fact, we define a duality gap to quantify the closeness between D star and P star. So we define duality gap. That duality gap is equal to P star minus D star. So if P star is equal to D star, so we say that the duality gap is equal to 0, and we refer to this case as a strong duality. And when P star is less than D star, so this case is referred to as weak duality. This strong duality usually holds for the case when the primal problem is a convex problem. So we say for primal convex problem, strong duality usually holds. So we cannot say that strong duality always holds for primal convex problems. So, so there are conditions under which strong duality holds for primal convex problems, and we refer to those conditions as constraint qualifications. So we say constraint qualifications. So constraint qualifications refers to the conditions under which strong duality holds for primal convex problems. And there are several conditions available in the literature uh, on the primal convex problems for which strong duality holds. And among those conditions, one very simple but powerful condition is a Slater's condition, or we call it Slater's constraint qualification. Let's look at this Slater's condition. So Slater's condition, also referred to as Slater's theorem or Slater's constraint qualification. So for a convex optimization problem, there is a typo here. This should be, in fact, AX is equal to B. Slater's condition tells us that strong duality holds if there exists some X in the relative interior of D, where D refers to the domain of the optimization problem, that is an intersection of the domain of objective functions, objective function and inequality constraint functions. If there exists such X such that AX is equal to B and inequality constraint function is less than 0. So here we do not have a weak inequality, rather we have a strong inequality, that we require that inequality constraint function should be less than 0 for X that belongs to relative interior of D. It simply means that there exists a strictly feasible X. So our Slater conditions informs us that duality gap would be 0 or strong duality holds if there exists a strictly feasible X, or we have an X for which inequality constraint function holds with strong inequality. You see here that this latest condition is a very simple condition, but it is very powerful and it is used very widely to show that the dual problem, the solution of the dual problem is equal to the solution of the primal problem when Slater's condition holds. So when inequality constraint functions are affine, we can further refine this Slater's condition. So it simply says that for a affine Fi, so that means this inequality constraint function is affine. If any of Fi is affine, we only require feasible X. It simply means we do not require strict feasibility. We only require a feasible X. Or mathematically, it simply says that for a affine Fi, we only require inequality constraint function to hold. Consequence of this refinement for a affine inequality constraint function is this, that when any Fi is affine, we just require the primal problem to be feasible for strong duality to hold. So when we have affine constraints, we say a strong duality holds when the primal problem is feasible. Let's look at one example in which we will formulate Lagrange dual problem for linear program. So we start with a formulation of a primal optimization problem that we want to minimize C transpose X subject to AX is equal to B, and we have inequality constraint that we require X to be greater than or equal to 0. So in the previous module we determined the Lagrangian function for this primal optimization problem, and we also computed the Lagrange dual function. So the Lagrange dual function for this primal optimization problem is given by g lambda mu, and this is a piecewise, and this is given by um, mu transpose b when c minus lambda plus a transpose mu is equal to 0, and this is in fact minus infinity otherwise. So since g lambda mu is, since Lagrangian is unbounded below when c minus lambda plus a transpose mu is not equal to 0, and therefore we have minus infinity. And when this c minus lambda plus a transpose mu is equal to 0, Lagrangian is constant mu transpose b, and when we take infimum over the Lagrangian, we get mu transpose b. So we have this Lagrange dual function, and we can formulate a Lagrange dual problem. So in Lagrange dual problem, we simply maximize this Lagrange dual function. So this is, since this is piecewise, so we maximize mu transpose b, so only this bit, and subject to this lambda should be positive, so lambda should be greater than or equal to 0, non-negative. And we should also have another constraint which is explicit here, and we will require that c minus lambda plus a transpose mu is equal to 0. So we require this a transpose mu plus c minus lambda should be equal to 0. So this is an explicit constraint here, and that comes from the domain of this Lagrange dual function. So we can equivalently write this dual problem as by combining inequality constraint and equality constraint. Since this equality constraint, we can write lambda is equal to a transpose mu plus c, and since we require lambda to be greater than or equal to 0, it simply means we require a transpose mu plus c greater than or equal to 0. So we can reformulate this Lagrange dual problem to maximize mu transpose b subject to a transpose mu plus c greater than or equal to 0. So this is a Lagrange dual problem, and we know when we solve this convex optimization problem, this is simply LP. So what you obtain is the maximum value of the objective function, we call it d star. And similarly, when you solve this primal LP, what you get is p star. And if we employ the Slater's constraint qualification here, so in primal problem, inequality constraint function is affine, and if the primal is feasible, Slater's constraint qualification guarantees that strong duality holds. When primal optimization problem is feasible, we say strong duality holds, or p star would be equal to d star, or duality gap is equal to 0. Now we look at one more example, that is least squares. So we start with a primal optimization problem. So we want to minimize x transpose x subject to ax is equal to b, and this matrix A belongs to Rp cross n, or we can say we have a p number of affine equality constraints. So B also belongs to Rp, and x belongs to Rn. When p is less than n, so ax is equal to b would give us infinite number of solutions, and among those solutions we want to choose the solution that has the minimum norm, or in fact that is the least norm, and therefore this this problem formulation is also referred to as least norm signal estimation, that you have B and you know A, and X is the variable you want to determine, and since P is less than N, there are infinite number of solutions for X, and among those solutions you choose the one that has the least norm. And so this is a primal optimization problem, and in fact this is QP, right? So you have a quadratic objective function and you have affine equality constraints, right? So for this primal optimization problem, we start with formulation of Lagrangian. So if we want to come up with a dual problem, but we will start with the formulation of Lagrangian. So we construct a Lagrangian, so L, X and mu, since we do not have any inequality constraint here. So we say Lagrangian is a function of X and mu. So mu is the variable that refers that is associated with the equality constraint. So Lagrangian is given by objective function X transpose X plus mu times equality constraint Ax minus B, right? So this is a Lagrangian. So using Lagrangian, we determine the Lagrange dual function first. So by definition, Lagrange dual function would be a function G mu, and that is given by so we minimize Lagrangian, or we take infimum of Lagrangian over X. So we take infimum of Lagrangian over X, and we know that this is Lagrangian is given by X transpose X plus mu transpose X minus B. And if we see this Lagrangian is in fact convex quadratic. So we can take gradient of this function to determine Lagrange dual function. So we note that this Lagrangian is convex quadratic, and we determine the gradient of Lagrange dual function, that is given by 2x plus A transpose mu, and we substitute equal to 0. So to determine x will be given by minus 1 by 2 A transpose mu, and when we substitute this x in the Lagrangian, we obtain the Lagrange dual function G of mu, that is minus 1 by 4 mu transpose A into A transpose mu minus B transpose mu. And you can see that this is in fact concave. So because A into A transpose would be always positive semi-definite, so mu transpose A into A transpose mu, so this term would be convex, and we have this negative sign here. So G of mu is in fact concave quadratic, and by definition we know that G of mu would be less than or equal to P star, or Lagrange dual function serves as a lower bound on the optimal value of the primal problem. This is the lower bound. So the question is, what is the best lower bound? So to determine the best lower bound, we formulate a Lagrange dual problem. That is, we maximize G of mu, and subject to, since we do not have any constraint here, so since we do not have any lambda here, and there is no restriction on the domain as well, so Lagrange dual problem is an unconstrained convex optimization problem in which we want to maximize a concave quadratic function that is given by minus 1 by 4 mu transpose A transpose mu minus mu transpose B. This is equivalent to if you minimize the negative of this, or which is a convex quadratic function. So you can solve either of these, and we can determine the optimal mu for which Lagrange dual function is maximized by taking derivative of this Lagrange dual function. So we take derivative of g with respect to mu, and what we get is minus 1 by 4 2a transpose mu minus b, and we substitute equal to 0 to obtain mu, and that mu would be minus 2a transpose inverse b. In fact, this is mu star because this is the optimal mu at which the Lagrange dual function is maximized. So when you substitute this optimal mu in the Lagrange dual function, so what we get is d star, or the best lower bound on p star. So d star will be given by d star is equal to g star, so g at mu star, and that is given by b transpose a into a transpose inverse b. And so this is our d star. We can also determine what is the optimal value for the primal problem. So let me quickly rewrite again the optimal. So the primal problem. So in primal problem we minimize a quadratic function x transpose x subject to ax is equal to b, and what we know that the solution of this is given by the pseudo inverse of a. So x star would be a transpose inverse b, and when you substitute this in on the objective function x transpose x, so what we get is p star. So p star would be x star transpose x star, and that is given by b transpose a into a transpose whole inverse into b, and in fact this is equal to d star. So we say that for this problem we have strong duality, and in fact this is also found by the Slater's condition or Slater's constraint qualification. Let us summarize this module. So for a primal optimization problem in which we minimize objective functions subject to some inequality constraints and some equality constraints, and this problem does not need to be convex. So for a primal optimization problem, we can formulate a Lagrange dual problem in which we maximize a Lagrange dual function subject to lambda greater than or equal to 0. So lambda is Lagrange multiplier or a dual variable that is associated with inequality constraint functions. So even when the primal optimization problem is not convex, Lagrange dual problem is always convex. And when we solve this problem, so what we obtain is d star, and the solution of the Lagrange dual problem, this d star is the best lower bound on the optimal value of the primal problem, that is the g lambda star mu star is equal to d star, and that is less than or equal to p star. And we also defined the duality gap, the difference between p star and d star. So duality gap is defined as p star minus d star. And then we also talked about the notion of weak duality and strong duality. So we say weak duality holds when p star is less than or equal to d star, and strong duality holds when p star is equal to d star or duality gap is equal to 0. Among the conditions that establish the strong duality, one very simple but very powerful condition is the Slater's condition or Slater's constraint qualification that establishes strong duality for convex primal optimization problem. We stop here and we will continue in the next module. Thank you very much.